Hello guys, welcome to my video. My name is Abulfaz Mahmoudpour, and in this video I'm going to solve the two-dimensional Laplace equation analytically in Cartesian coordinate, and this is nothing but the second order partially differential equation like this. So we have our differential equation, and we will use the separation of variable, and I define the u, that is function of x and y, equal to the vx multiple to the wy, and here v is just a function of x, and the w is just a function of y. So if I substitute it here, so first let me calculate the first derivative of u with respect to the x, and this is simply the first derivative of v with respect to the x multiple to the wy, and the second derivative of u with respect to the x is second derivative of v with respect to the x multiple to the, again, wy. And for sake of simplicity, I here define the second derivative of v with respect to the x with vxx. And again, if I calculate the second derivative of u with respect to the y, it will be simply vx multiple to the second derivative of w with respect to the y, and this is nothing, just v multiple to the wyy. And if I substitute this one and this one in my differential equation, so I have vxx multiple to the w because plus v multiple to the wyy equal to 0. And if I bring this part to the right hand of equation, it will be vxx multiple to the w equal to minus v multiple to the wyy. And if I divided both sides of this equation with wv, what I have is just vxx divided by v equal to the minus wyy divided by w. And if I put this equation equal to a parameter, and I call it parameter with lambda, so we will have two independent differential equation, vxx minus lambda v equal to 0 and wyy plus lambda w equal to 0. So let's solve this individual differential equation. So we can imagine different condition when lambda is equal to 0 and when lambda is a positive 0. For the case of lambda equal to 0, this term is 0 and also this term is 0. So what we have is just the second derivative with respect to the x equal to 0, and we know that any linear function satisfies this equation. And also for w, when lambda is 0, a linear function in this form satisfies this differential equation, because first derivative, for example, in vx, first derivative of vx with respect to the x is just c1, it's a constant, and the second derivative will be equal to 0, and this satisfies this equation, and also this equation satisfies this one. And if we imagine the other case when lambda is a positive 0, for this differential equation we can have a solution in the form of exponential of sigma y. So let's check it, and let me put this solution in this differential equation. So the first derivative will be the sigma multiple to the exponential of sigma y, and the second derivative will be the sigma square multiple to the exponential of sigma y. And if I substitute here, I have sigma square multiple to the sigma exponential of sigma y plus lambda multiple to the exponential of sigma y. And if I divided both sides of this equation with exponential of sigma y, I will have sigma squared plus lambda equal to 0, and finally I will find sigma equal to plus minus square root of minus lambda. And if I substitute here, I know that for two cases, when sigma is minus square root of minus lambda and when sigma is plus square root of minus lambda, any linear combination of both possible solution also can be the solution of this differential equation. I mean, when wy is just linear combination of this function and this function, so it also can satisfy this differential equation. And again, here I can imagine two cases when lambda is less than 0 and when lambda is greater than 0. For the case of lambda less than 0, I define new parameter and put lambda become equal to minus omega square. And if I substitute lambda here, what I have is just wy equal to c1 exponential of omega y plus c2 exponential of minus omega y. And for the case of lambda less than 0, what I know that minus 1 here is just I squared, and this I is imaginary number. And if I substitute minus 1 with the square root of imaginary number, what I have is just c1 exponential of minus I square root of lambda y plus c2 exponential of minus I square root of lambda y. I did nothing, just I put minus 1 with I square, and I bring out I square from the square root, and it will become I. So let me simplify this solution more. I want just express this this function with sine hyperbolic and cosine hyperbolic. So we know that exponential of omega y can be expressed in the form of cosine hyperbolic omega y plus sine hyperbolic omega y, and exponential of minus omega y can be expressed in the form of cosine hyperbolic omega y minus sine hyperbolic omega y. And if I bring the cosine hyperbolic out of bracket and keep c1 and c2 inside bracket and simplify it a little more, we will have cosine hyperbolic omega y multiple to c1 plus c2 and sine hyperbolic omega y multiple to the c1 minus c2, right? And if I define new parameter with a and b, c1 plus c2 equal to a, c minus c2 equal to b, so I have wy equal to the a multiple to the cosine hyperbolic omega y plus b sine hyperbolic omega y, and a and b is just a constant number. And for those who don't know how this cosine hyperbolic and sine hyperbolic looks like, I draw it here. This is cosine hyperbolic of z. This is sine hyperbolic of z. And you see that when z, the argument of cosine and sine hyperbolic and cosine hyperbolic is 0, sine hyperbolic is 0, and cosine hyperbolic is 1. And you see that cosine hyperbolic is an even function, but sine hyperbolic is an odd function. And I want to also simplify the wy for the case of lambda greater than 0, and I want expressed then in the form of cosine and psi. And we know that exponential of I square root of lambda y is just cosine of square root of lambda y plus I sine square root of lambda y. And exponential of minus I square root of lambda y is just cosine square root of lambda y minus I sine square root of lambda y. And if I simplify it more, I have cosine square root of lambda y multiple to the c1 plus c2 plus sine hyperbolic of lambda y multiple to the ic1 minus ic2, and I bring this I out of parenthesis. So, and again, if I define the new parameter a equal to c1 plus c2, b equal to ic1 minus c2, and define lambda with omega square, and substitute this here, I will end up with this equation. Wy is a cosine omega y and plus b sine omega y, right? And if I summarize what I get for this differential equation, the solution of this differential equation for different case of lambda, what I summarize it here. So we saw that for the case of lambda less than 0, the solution of this differential equation can take the form of cosine hyperbolic and sine hyperbolic. For the case of lambda equal to 0, it take the linear form, which could be a constant, and I put this constant with 1 for simplicity, and this could be y or the linear combination of this. And for the case of lambda greater than 0, we found out that omega y, wy can take the form of cosine omega y and sine omega y. And if we look at these equations, this partial differential equation, we see that they are differ just in the sign of lambda. So when we found out that the solution of this function for the case of lambda less than 0 is cosine hyperbolic and sine hyperbolic, so the solution of this when lambda is less than 0 should be in the form of sine and cosine, right? And when, for the case of lambda greater than 0, the solution of function for this is cosine and sine, here lambda is greater than 0, but here this is less than 0. So the solution of this function should be in the form of cosine hyperbolic and sine hyperbolic, right? But for the case of lambda equal to 0, both are the same. They are just a linear function. And so we have wy and we x here, and u is just their multiplication. And any possible multiplication of w and v, I just write here. In the case of linear, it could be 1, x, y, and xy. I write it here. And for case of lambda less than 0, we can have cosine omega x multiple to the cosine hyperbolic omega y, sine omega x multiple to the sine hyperbolic omega y here, or cosine omega x multiple to the sine hyperbolic omega y here, or sine omega x multiple to the cosine hyperbolic omega y here. And again, I just write the possible multiplication of w and v, and we have this solution for u in the case of lambda greater than 0. So we solve this two-dimensional Laplace equation analytically, and we found out that it can have large number of solutions for different conditions. So in order to restrict ourselves to an explicit solution, we should have some boundary condition. Without boundary condition, we see that there is large number of solutions for our differential equation. Now, I want just define some boundary condition and restrict our solution to some area and define boundary condition. In other words, I want to solve two-dimensional Laplace equation in this area, and the value of function at the border, at the boundary, is well defined. And I just define like this: when x is equal to 0 for any y, here the value of function is equal to 0. At the lower boundary, I define like this: when y is equal to 0 for all x, the function of ux is 0. At the upper boundary condition, when y is equal to b for all x in the interval from 0 to a, we have this value for function sine omega x divided by sine omega a. And at the right boundary, when x is equal to a for all value of y from 0 to b, the function should be in the form of, not should be, I just define it to be like this. So it is sine hyperbolic omega y divided by sine hyperbolic omega b. So what does it mean? At the left boundary, when this is 0, it means that v0 should be 0. At the upper boundary, when this is equal to this, it means that vx is equal to the sine omega x divided by sine omega a. And when y equal to b, wb is equal to 1. And at the lower boundary, again, we have w0 equal to 0 when y is 0. And at the right boundary, when x is equal to 1, va is 1, and wa, as I mentioned, for all value for y from 0 to b, it should in the form of sine hyperbolic omega y divided by sine hyperbolic omega b. So let's apply this boundary condition and see how our solution looks like. So we found out that for lambda less than 0, the Vx should be in this form of cosine and sine. For lambda 0, it should be a linear form, and for lambda greater than 0, it should be in the form of hyperbolic, cosine hyperbolic and sine hyperbolic. So at the left boundary condition, we say that V0 is 0. So I just put x equal to 0. It's a cosine 0, b sine 0, c0 plus d, e cosine 0 plus f, e cosine hyperbolic 0 plus f sine hyperbolic 0. And we know that cosine 0 is not 0. It is 1 in order to satisfy this condition. So a should be 0. And also we see that from this, d should be 0. And again, cosine hyperbolic omega 0, as we saw, when argument of cosine hyperbolic is 0, it is not 0. This is again y. And in order to satisfy this condition, this coefficient e should be 0. So a and d and e should be 0. And if substitute here, what we get is just, okay, b sine omega x for lambda less than 0, cx for lambda greater than 0, and f sine hyperbolic omega x for lambda greater than 0. And let's apply the other boundary condition, and we saw that, and we defined that at the upper boundary condition, the value of function for all x should be in the form of sine omega x divided by sine omega a, right? And if we put it equal to our function, we see that in order to satisfy this condition, if you look at here, we have sine omega x here and sine omega x here. And we can simply conclude that b should be 1 over sine omega a. And the c should be 0. Here you should be careful, because although this equation may have some solution in some specific point, but we need to be satisfied for all x, not in a specific x. It should be satisfied for all x from 0 to a. And in order to satisfy this condition, c should be 0 and also f should be 0, because again, sine omega x and sine hyperbolic omega x have some solution in some specific point, but they are not same at all x. So what we found is just c and f should be 0 and b should be 1 over sine omega a. So we found this value, this function for Vx. It should be sine omega x divided by sine omega a by applying our boundary condition. And if we recall the summary of solution for this differential equation, so applying boundary condition, we conclude that Vx can only take the form of sine omega x. What does it mean? It means that cosine omega x is not acceptable for this boundary condition. And also linear form is not acceptable. And also cosine hyperbolic and sine hyperbolic is not acceptable when we have the boundary condition that we defined it. What does it mean? It means that in ux, that is just multiplication of v and w, when we cannot take the linear form, when we cannot take the cosine hyperbolic and sine hyperbolic form. So in the solution for u, the solutions that has the cosine hyperbolic term and sine hyperbolic term cannot acceptable. We see that all term has either cosine hyperbolic or sine hyperbolic here and here. So none of the solution is not acceptable for u. And when it cannot take linear form, so 1 and x cannot acceptable. Moreover, xy cannot acceptable because we cannot be in the form of x. And here, the solutions that the term of cosine omega x, like here and here, is not acceptable. And here, right? So what do we have here? Here, we see that the value for omega, the value for wy can only take the form of sine hyperbolic, can only take the form of either sine hyperbolic or cosine hyperbolic. So what does it mean? It means that cosine and sine form cannot be acceptable for wy, right? And also, the linear form cannot be acceptable for wy. And the only acceptable form after applying boundary condition for Vx is in the form of sine, and for wy is in the form of cosine, either cosine or sine. So in order to find which is acceptable, let's apply the boundary condition for wy. Let's apply the boundary condition for wy, and also when the wy cannot the form of linear, also this solution, this y, cannot be acceptable for u. So if we apply the boundary condition for wy, that we understand that it should have the form of cosine hyperbolic and sine hyperbolic. So at the 0, when y is 0 at the lower boundary, we define that the value of function should be 0. So again, this is not 0. So in order to satisfy this condition, a should be 0. And when a is 0, we have just wy equal to b sine hyperbolic omega y. And at the right boundary condition, we define that for all value from 0, for all value for y from 0 to b, at this boundary, the value of wy should be in the form of sine hyperbolic omega y divided by sine hyperbolic omega b. And this is equal to this our function. I put just the boundary condition here. And from this, we can easily see that b can be in the form of 1 over sine hyperbolic omega b. So after applying boundary condition, we found the solution, and this is just multiplication of vx multiple to wy. We found sine omega x divided by sine omega a for vx, and we found sine hyperbolic omega y divided by sine hyperbolic omega b for wy. And this is solution of two-dimensional Laplace equation in Cartesian coordinate with well-defined boundary condition. At this point, I want to plot the function u from 0 to a and from 0 to b, and let's see how does it look like. So for plotting, I will use MATLAB. I have MATLAB opened here, so I define the new editor file. So I start with CLC. It just clear the command window. Clear, it's clear the cache. And close all, it's clear all. Open figure in MATLAB. So here, for simplicity, I put omega equal to 1, so I don't take into account this omega, and imagine that omega here is 1. So, and I define the a to be equal to, let's define it to be 3 pi, right? And I define b to be equal to just pi. It could have any number, no matter. I just define 3 pi and pi for a and b, right? So I want to define the number of point in x direction with 100 number of point in y direction with 50 number. Just as define the number of points that I want to plot this function in these points, right? So the step value in the direction of x, I define it with dx, and this should be a divided by nx, right? And the step point in the y direction, I define it with dy. It should be just b divided by ny, right? And so I should define the interval for x. X should be changed from 0 with step dx until a, right? And y should be changes from 0 with a step dy until b, right? Okay, so let's save this program somewhere. I just name it with test, just test, save. Okay, so let's run to see everything is right. Yes, everything is right. Okay, I ran this program, and I defined here x as a linear array. it's a linear array, and also y is linear array. But we know that our function, that is u, what is this? This is sine of x divided by sine of a multiple to the sine hyperbolic of y divided by, I should put it here, dot divided, because when we have not a scalar in the multiplication and division, we should have a point at the side of multiplication or division. So, and this is sine hyperbolic y divided by sine hyperbolic b, right? And let's plot it in this 3 dimension, and I use surf command, surf u, and let's run it. It doesn't work. Why? It says that dimension must be agree. How? Because if you look at this, this is just a linear array, and also y is just a linear array, but our u, our function, is just a rectangular array. It's a matrix. Yes, it's a rectangular array, and we can draw this function in 2 ways. Just find the number of the value for u in a loop, or just by definition new variable that convert the x and y to the rectangular array from the linear array. And I just do it with the command x. I just define new variable that is rectangular matrix with capital X and capital Y equal to the, using mesh grid command, we can convert the linear array to the rectangular array, and just convert the linear array of x and y to the rectangular array, and this is x, y, right? So let's see now. Here also, so I have new variable capital X and capital Y. Let's run it. Yeah, you see, it's run. Now, if you look at the size of x, and that give you the dimension of your matrix, and this is one row and 101 column. But if you look at the size of u, this is 51 multiple to the 101. That's why we had the error of mismatching in dimensionality between x and y. So that's why we defined this command to change this linear form for x to the rectangular form. And if I look to the size of capital X, it should be in the same dimension with u. You see, both is 51. Size of u is 51 multiple to the 101, and also x, size of x is 51 to 101. And so we see that the solution for the solution of second two-dimensional Laplacian coordinate in Laplacian function in Cartesian coordinate looks like this. Let's make it a little beautiful. First of all, I want to plot it in a normalized form. I just define normalized u, and so first I should find the maximum of max u, the maximum of matrix. You can do it by the command max, the parentheses, and it should be u, an empty bracket, in all column and in all column and rows, and I normalize any u to the maximum value of u. So nu normalized u is just u divided by max u, right? And let's plot this time normalize u, and you see the maximum. I normalize this function to its maximum. And if I want to make it more beautiful, let's define color map. Color map, what is it? Color map. Color map. I choose the jet family. It's just a family of color. You see? F5, a color of our plot change. And I don't want to have this black line, so if I use the command shading in terp, it will clear shading in terp. It will clear this black lines. And here, the family of jet, we can choose the number of color that we want to have in our plot. If I choose 1, it will be plotted in just one color. You see, this is 1. If I choose 2, F5, 2 color, 3 color, so on and so forth, 10 color, right? I have 10 color here. And the maximum value for the jet family is 256. Yes, and F5, you see it's become a little more beautiful. And this is our function for u when x change from 0 to a, 0 to 3 pi, and b change from 0 to pi. And here I just plot this function in the number of point, no matter. It's possible to convert the plot in the real coordinate from 0 to 3 pi. But here you see this is from 0 to 101, and from 0 to, it should be somewhere from 0 to 51. And if I want to plot it in 2 dimension, I just use contour F. Contour. Okay, let's use first the contour. Contour normalized view. And let's define a new figure. Yes. Let's bring it a little up. Okay. And in new figure, I want to draw this function in 2 dimension, and I use contour normalized NU. And you see, this is contour. It's draw our function in a contours form, right? And okay, and if I put an F here, it will fill the space between the contours with color. You see, now we have color here, and I want to have the same color map, so I just copy here and paste it here. I want to have the same color, you see, and I don't want to have this line, but before deleting this black line, if you add the number here, it will show you the number of contours. So if I put here in the contour FNU 1, if I put 1 here, we will have just 1 contour. And if I put 2, the number of contours increase, you see. And I put it 200, you see, number of contours increased. And I don't want to have this black line, so here I define the line color. And I define the line color here to be none, right? Now I don't have this black line, and this is in 2 dimension, and this is in 3 dimension. And we solve the Laplace 2-dimensional Laplacian equation in Cartesian coordinate analytically. That's it. I hope you enjoyed my video. At the next video, I'm going to solve the same problem numerically using the finite difference method. And again, Like previous video, I want to compare the analytical solution and the numerical solution and see how much is error between two methods, and we will see how we can reduce the error. So if you like this video and you don't want to miss the next video, please don't forget to like and subscribe my channel to be away from the upcoming video. Thank you very much.